All right, guys, welcome. We're going to talk about what a wave actually is as we enter into Unit 11, which is waves and two common types, sound and light. We'll focus on those two more than others. So, what is a wave? A wave is a disturbance in matter, or not, as we'll see in a minute here, that carries energy. A disturbance just meaning motion, a motion that carries energy. So, waves carry energy through matter or space. Matter is things like solid, liquid, and gas. Space would be an absence of those things. So outside of our planet's atmosphere, between us and the sun, unless you run into another planet, you're not seeing a lot of matter. If there's an absence of matter, we call that space. Most waves require a medium, such as solid, liquid, or gas, to travel through. And the matter that it's traveling through, that is the medium. So whether it's a solid, liquid, or a gas. And mechanical waves are a type of wave that require a medium. Light is an example of an electromagnetic wave that does not require a medium. They consist of a changing electric or magnetic field caused by a disturbance or motion of a charged particle. So light waves are electromagnetic waves. These do not require a medium. And these are a back and forth electric or magnetic field, so same type of motion, which we'll talk about in a minute, which radiate outward really, really fast when an electric or charged particle moves. So waves, two types, mechanical and electromagnetic. This is a good review for us. It's also a good place to pause and just remind you that if you didn't, it's okay when we're on a previous slide to pause so you can finish the notes. And these are posted in the sheet or right above the video here on Schoology, or you can write them on a separate sheet of paper. We got two types of mechanical and electromagnetic waves. Longitudinal and transverse are two types of mechanical. We'll talk about what they have here, or sorry, the unique portions of them. And electromagnetic, we got a big spectrum of them here as well. So waves, big idea here is they transfer energy, and that energy spreads out over time, right? So when my vocal cords vibrate, it causes vibration and movement of air particles, and then that goes out, which is why I can hear it. This computer can record it, but as you're sitting in your home, you couldn't hear me speaking because that energy spreads out and is lost or transferred. Because energy can't be created or destroyed, remember, but it can be transferred. So waves are related to vibrations. So again, my vocal cords vibrate. That's the object. Causes vibration of air particles and movement of energy through the medium of air. So electromagnetic waves are charged particles that are moving, and mechanical wave, the particles also vibrate as they pass through the medium. And that is a change or transformation of energy. So we could think of this example, and I'll come back to that slide in a minute, of what's happening to our particles in a medium. So as a wave, which is moving left to right here, hits that particle, it causes the particle to move up and down. So this spring, as I pull it down, would just go back up and down, up and down, up and down, up and down, until eventually it comes back to the place where it initially was, right, a neutral position. But as it does that, it causes energy to be transferred into the spring next to it, up and down, 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 so to speak. And that's how waves move. As a particle moves, it transforms that energy, it transfers it, causing what we call simple harmonic motion. So that this would be a good example of a transverse wave. And eventually that vibration would fade out, and it's called dampened harmonic motion. So we can think of particles moving just like that, except, and we'll see a better visual of that in a little bit, but this is the main idea that we're starting with. So particles can either vibrate up and down or back and forth, and the direction they vibrate determines whether it's transverse, if the particle is moving left to right, up and down. Okay. That it's perpendicular. That's the piece about transverse waves. Longitudinal is the same direction. So you got L and L here, same direction, same direction. And that's the way the particles are vibrating as it relates to the motion of the wave. So lights are transverse wave, light waves are, sorry. And the big idea is they are perpendicular, just like a T is called perpendicular. So if we look at this common example of a transverse wave, you see as the wave is moving left to right, the particles move up and down. Big piece is the top of a wave is called the crest, bottom is called the trough. The amount of displacement or change from its initial starting position, this dashed line, is called amplitude. You can measure it from middle to bottom or middle to top, it's the same. And wavelength is either how the distance it requires to go to the same spot on the wave. So notice same spot crest to crest, same spot trough to trough, or midpoint. That doesn't count because I haven't gone full up or down yet to midpoint. Now mechanical waves, the two types as we saw, we got transverse waves here. Here you see particles actually moving. As the wave moves this direction, what you see is that you have an up and down motion of particles. The particles are displaced. If I'm looking at this one right here, it goes up and then down, up and then down, up and then down. And that's a transverse wave. But if I look at a longitudinal wave, such as sound, as I look at a particle, it moves left to right, left to right, left to right. Okay, so we still measure wavelength or amplitude, which just looks a little bit different in a longitudinal wave. So longitudinal waves, the particles are parallel. So what I see here, as the wave moves this way, the particles also move in that direction, left to right. You'll notice this area of high density, called the compression, area of low density, called the rarefaction. We'll talk about how to measure wavelength on a longitudinal wave as well. So sound is the most common example of that. Feel free to watch this link. I'm not going to spend the time to look at it now, but it's in the PowerPoint presentation that's uploaded to Schoology. So surface waves, particles move both up and down and side to side when there's a boundary between different types of mediums, such as water and air. Boundary between two different mediums causes a circular motion. That's a unique characteristic of surface waves. So one thing to note, waves are disturbance that transmits energy. You got two types, mechanical and electromagnetic. All of them carry energy, and just as different types of mechanical waves will have different amounts of energy, electromagnetic waves, you also have different amounts of energy. You got a lot of energy, UV light, sunlight, that can damage your skin, causing sunburn or skin cancer. You got radio waves, which cannot. Microwaves, which cannot. They do not have enough energy in order to do that. And then in our visible light spectrum, you also have different colors from red to violet that have different amounts of energy, red being the lowest, violet being the highest. So now that you've taken the notes, I want you to just take some time to do the homework here, and then tomorrow you'll have an activity based off of those problems. So if you have questions, email, and we'll set up a time to chat. Okay, love you guys. Have a great day. Bye.